you all for joining us here in Zoom. We're gonna go ahead and get started. Oh, I see a few more people trickling in. Okay. Well, thank you all for joining us tonight. My name is Sarah Sugi Dono, and I will be your MC. Tonight, we are joined by Andrea Kealoha of the Department of Oceanography at the University of Hawaiʻi at Manoa. So thank you, Andrea, for being here with us. Tonight, she'll be presenting preliminary data from water quality sensor deployments and discrete water quality sampling events that she's conducted over several months, including after significant runoff events, and sharing initial insights into the effects of the Lāhainā Wildfire on coastal water quality in West Maui. Before we get to all of that, we would like to say mahalo to the County of Maui, one of the sponsors that makes this talk possible tonight. If you don't know, we do host a monthly speaker series the first Wednesday of every month, typically at 5:30 on Zoom. So if you are interested in attending any of our future talks, stick around and we'll have a link so that you can be notified of future events. And I think we'll also drop that link into the chat. You can sign up for our email list. So who are we? We're Maui Nui Marine Resource Council. We're a 501c3 nonprofit, and we're celebrating 16 years of working for clean ocean water, healthy coral reefs, and abundant native fish. And our work takes many forms. We do work Malka to Makai. So we have our Hui o Kawaiola water testing, community-based water testing program. This includes, sampling at 39 plus sites around Maui County, and also being a part of the first flush responding efforts to capture some of the runoff in these burn zones to see, what impact it may have had on our nearshore waters. We've also brought cutting edge technology to survey the coral reefs, underwater technology, so that we can compare the health of the reefs prior to the fires, or prior to runoff, excuse me, and after the runoff. And we've also created the first ever Hawaii-focused reef-friendly landscaping program, and sort of course and certification program, hoping to kind of nip that problem in the bud. A lot of our problems for our reefs do start onshore, so trying to get to the root of the problem instead of only addressing the symptoms. We also have a dive team that regularly monitors the health of local reef and fish populations. So as you can imagine, protecting our natural resources, it takes a lot. And so, if you would like to join us, your support here means a lot. If you would like to support us financially by making a donation or learning more about us, you can always go to mauireefs.org and check us out there. So a few notes before we introduce our speaker. We will have time at the end of the presentation for question and answers. So please submit your questions by using the Q&A button on the lower edge of your Zoom screen to do that. Unfortunately, we're not on Facebook tonight, just a few more technical difficulties. But this presentation is being recorded, and once Zoom does its thing, we always upload it to our YouTube channels, which is at Maui Reefs. So it will be available for viewing after tonight, or for whatever reason some of your friends couldn't make it. Okay, so now the reason why we're all here tonight for our speaker. Andrea was born and raised in Paia, and she obtained a BS in Global Environmental Science at the University of Hawaiʻi at Manoa, and a MS in Marine Science at Hawaii Pacific University, and a PhD in Oceanography at Texas A&M University, where she studied the impacts of global climate change stressors such as ocean acidification and hypoxia on coral reef health. In 2018, she returned to Maui and opened the Water Quality Lab at UH Maui College. In August 2023, she accepted an assistant professor position in the Department of Oceanography at UH Manoa. Andrea's still based on Maui and is passionate about conducting research that explores fundamental questions related to coral reef ecosystem function and addresses local challenges relevant to the Pacific Island communities. So that was a lot. We're very excited to have Andrea. Andrea, mahalo for being with us tonight, and the floor is all yours.
Okay, can you hear me?
Yep, we can hear you.
I'm gonna share my screen. Okay. Can you see my screen?
Yes, can see your screen.
Okay.
Perfect.
Great. Okay. Well, hi, everyone. Thanks for coming to this presentation tonight. I know this topic is really important to our community, and so I'm just glad to be able to share these results with you. We've spent the last 6 months collecting a lot of data. We have thousands of measurements, hundreds of water samples, many that still need to be analyzed. And so I'll say that these results are preliminary. The study, is ongoing, and we're still really in the early stages of trying to understand what these data are telling us. But hopefully, this presentation can provide some kind of preliminary insights that we can use to guide more targeted monitoring work moving forward. So yeah, my name is Andrea Kealoha. I study coral reef stressors. The other PIs on the project are Nick Hako, who's also an assistant professor at Mānoa in the Department of Oceanography, and Nick studies metals. Eileen is in Sea Grant, and in the context of this study, she's studying contaminants, and she's also leading the contaminants in fish component. And I believe Eileen is on here, so she might be able to answer some questions later if there's any, questions about contaminants. And then Craig Nelson, I believe, is also on, and Craig's professor in the Department of Oceanography, and he's a microbial ecologist. And I also want to acknowledge the many partners that we have on this project. As you can imagine, we've collected a lot of data in areas that were challenging to get to. And so, it's really an effort of a broader group. And so we're just very grateful to all of our partners. So it's not always the case that I'm talking to or presenting to a conservation-minded community. And so I always start with the importance of coral reefs. So coral reefs are one of the most biologically diverse ecosystems on the planet. They provide food for hundreds of millions of people across the world, particularly in developing countries. They provide coastal protection. So it's estimated that coral reefs dissipate about 97% of the incoming wave energy. So if we didn't have coral reefs, our coastlines and our coastal infrastructure would be more inundated with storms and waves. They hold economic value, and we really feel this here in Hawaii through tourism and fishing. And then they hold cultural significance, not just in Hawaii, but across the Pacific. However, coral reefs face both global and local stressors, and global stressors are primarily driven by the burning of fossil fuels, which release carbon dioxide into the atmosphere. And when that happens, a couple of different things happen. One is that carbon dioxide is a greenhouse gas, and so it causes our atmosphere to warm. And then the oceans absorb some of that heat to help regulate the climate, so our oceans warm. The oceans also absorb some of that excess atmospheric CO2, and CO2 is an acid, so that makes the ocean more acidic. As the oceans warm, we start to see more coral bleaching. So corals have these symbiotic algae called zooxanthellae, and zooxanthellae give corals their color, but they also provide corals with the majority of their food source. So when the corals bleach, the algae are expelled, leaving these corals looking bleached, but also leaving them without food. And so they have to find other ways to get food. I refer to ocean acidification as the osteoporosis of the sea. So acidification gets at the shells and skeletons of calcifying organisms. So clams, oysters, and corals. So acidification weakens the structure of the reef. We also have local stressors to coral reefs. So the first is nutrient pollution. And primarily this comes from agriculture and wastewater. For Maui, the relative importance of these sources changes depending on where you are on the island. So, for example, on the North Shore, we have a lot of historical sugarcane production, and sugarcane took a lot of fertilizers. So the nutrients from those fertilizers percolate into the groundwater, and then the groundwater is released in the coastal ocean. So On the North Shore, we often can detect higher levels of nutrients. In West Maui, at Kahikili, we see the impact of treated injected wastewater. So at very localized spots at Kahikili, we can measure high, for example, nitrate concentrations associated with wastewater. Hypoxia is referred to, or means low oxygen, and hypoxia is usually preceded by nutrient pollution. And we often also see it with coastal acidification, particularly in the bottom waters where corals lie. And then sedimentation is something that we're really familiar with, especially, in South Maui, and given some of the recent Kona storm events. So together, these stressors can cause an array of negative impacts to coral reefs, including reduced growth and calcification, increased calcium carbonate dissolution, reduced recruitment, and over the long term, shifts from coral to algal-dominated reefs. And this is actually, I'm gonna just put on my little, sorry, I'm trying to find my laser pointer here. This figure on the bottom was sent to me by Mark Dicos, and it's an image showing a big plume of brown water that I think is released at Kahoma Stream following one of the recent January storm events in West Maui. Something that we haven't thought too much about is wildfire impacts to water quality and reef health. But with climate change, we expect to see an increase in temperatures, increase in droughts, as well as an increase in the intensity of hurricanes, which can drive strong winds. So this figure is showing the percent increase in wildfires under the RCP 2.6 scenario and RCP 6.0 scenario. So this is a low carbon dioxide emissions and high carbon dioxide emissions. And what we're seeing in both cases is up to an increase in 50% in wildfires by the year 2100. So basically, even if we reduce our emissions and the world only warms by 1.5 degrees Celsius, we'll still see a significant increase in wildfires. And of course, this has important implications for management. There's been some work looking at the impacts of wildfires to ocean ecosystems. So this photo on the top is showing wildfire aerosols released into the atmosphere over Australia, and then this big plume of iron-rich dust that's then deposited into the open ocean South Pacific. So many areas of our ocean are iron limiting, and so the addition of iron can help to stimulate algal blooms. And that's what's being shown here in this bottom figure. So this is showing the chlorophyll A relative anomaly in percent. And chlorophyll A is a proxy for plants or phytoplankton. So the red area indicates that there's this kind of big algal bloom following the addition of iron-rich dust associated with the Australian wildfire. In 1997, there was a catastrophic reef death in the Mānoa Islands in Indonesia, where 100% of the corals died. And this coral death was coincided with a strong upwelling event. And so upwelling brings cold, deep, nutrient-rich water to the surface ocean. The upwelling event, combined with drought conditions that sparked wildfires in Indonesia, was hypothesized to lead to a red tide. So the wildfires added iron into the surface waters. And red tides, you often hear about them in the Gulf of Mexico or in Florida. This is a type of harmful algal bloom. And so they hypothesize that these algae release toxins into the water that then caused reef death, or potentially the algae died, they respired, that process consumes oxygen, and this led to hypoxia. In Guam, people use fires to clear land or to hunt, particularly in the southern part of Guam. And this has led to accelerated erosion upland, which then causes high turbidity and increased sedimentation in coastal waters, particularly in the wet season when it rains a lot. So using coral cores, which are kind of like tree rings, they contain a historical record of coral growth. This study found reduced coral growth rates during times of high sedimentation. So here they're linking wildfires to increased sedimentation and reduced coral growth. And this has implications not only for Lahaina, but also for the reefs on South Maui that may potentially be impacted by sedimentation from the Kula fire. So to summarize what we know so far about wildfires to ocean ecosystems, we know that wildfire aerosols release iron and can stimulate phytoplankton blooms, and we saw this particularly in Australia. In a coral reef in Indonesia, local physical processes, so specifically upwelling, combined with the addition of iron from wildfires, led potentially to a harmful algal bloom and hypoxia, or low oxygen on the reef. And in Guam, the clearing of land through fires increases sedimentation and reduces coral growth rates. So when trying to understand the impacts of the Lāhainā wildfire to coral reefs and water quality, we don't really have a perfect analogy because as far as we know, there's never been an urban wildfire adjacent to a coral reef. So we know that rural fires can lead to sedimentation, hypoxia, and algal blooms, but what happens when you also release contaminants associated with urban infrastructure? So the kind of potential stressors that are on our mind and that we're thinking about and measuring are reduced water quality, enhanced nutrients and turbidity, possibly combined with hypoxia and coastal acidification, particularly after runoff or rain events, and then urban wildfire contaminants. So polycyclic aromatic hydrocarbons and PCBs, so the organic contaminants, as well as metals. So we applied for a National Science Foundation rapid grant following the fires. These grants are 1 year and they're designed to collect perishable data and answer ecological questions. So that's why we're focusing the study on coral reef health. We received the grant fairly quickly and mobilized for our first official sampling campaign in October, although we had been collecting water samples kind of opportunistically before that. We have 11 routine sites that we sample, plus some opportunistic sites, especially following rain and runoff events. And then we also have this offshore transect as well. We have a number of sites within the burn zone here, and then we have 2 control sites located north at Kahikili and south at Olowalu. And so far, we've done 5 sampling campaigns, including a couple that were after some storm events. So what are we collecting data for? I'm a carbonate chemist, so we're collecting carbonate chemistry, which tells us about acidification. So it's pH and inorganic carbon. We're also collecting nutrients, so the standard nitrate, phosphate, silicate, ammonia, and nitrite. We're also collecting metals, and I'll show you some data for copper, lead, and zinc today. Craig's group is collecting organic contaminants, PAHs and PCBs, as well as microbial communities and coral stress metabolites, which are indicators of coral health. We've also deployed about 20 sensors across 7 West Maui sites. So we have 5 sites within the burn zone: Waiakuli, Kahoma Stream, right outside of Kahoma Stream, Baby Beach, Lahaina Harbor, and Puamana. And then we have the 2 control sites, north Kahikili and south at Olowalu. These sensors were deployed in early November, and we pulled them out on February 1st. And these sensors are really important because they collect high temporal resolution data. So we have a measurement every 5 minutes for about 3 months. And these data are complementary to the water sample data. Something I think really unique about this study that I've never experienced before has been our collaborations with industry. So instruments are really expensive. And so we've collaborated with several companies who've either loaned us equipment or donated equipment. So we have two seabird hydrocats that were loaned to us. These were deployed, one outside Kahoma Stream and one at Baby Beach, and they measure temperature, salinity, oxygen, turbidity, pressure, and chlorophyll. And you can see them here, and also how much biofouling occurs after just a couple of months. Sea and Sun Tech, which is a company in Germany, loaned us 12 sensors, CTD48MCs. That's what's shown here. They kind of look like little torpedoes. And they measure temperature, salinity, oxygen, and chlorophyll. Precision Measurement Engineering actually donated 3 mini dots to us, which you can see here. These measure temperature and oxygen. And then we also deployed 7 tilt current meters, which are shown here. And these are measuring water speed and direction. So we have the water samples, we have the instruments. We also deployed auto samplers. So we had 4 deployments, one at Kahikili and Mala each. These auto samplers are programmed to collect water samples every 3 hours for 3 consecutive days. So they're measuring carbonate chemistry. And the auto samplers are really helpful because logistically, it's very challenging to collect samples at night on the reef. And so these auto samplers are a really great tool to catch that nighttime chemistry signal. A lot of really important processes happen at night. So the auto sampler data will help to give us the reef health metric, which is called coral reef metabolism. So reef ecosystem metabolism is also referred to as the metabolic pulse of the reef. It's the heartbeat of the reef. And it's composed of 2 different processes. So the first process is the breath of the reef. This is the photosynthesis and the respiration. And the second process is the growth of the reef, or the formation of the reef structure. And it can either be calcifying or dissolving. The growth of the reef is connected to the breath of the reef. Like, the growth depends on the energy created by the breath. And so it's really helpful to be looking at these 2 processes together. A healthy reef photosynthesizes more than it respires, or these processes are fairly balanced. And a healthy reef grows or calcifies more than it dissolves. So we know how these processes change the chemistry. I'm a chemical oceanographer, so this wouldn't be a presentation for me without some chemical equations in here, but we can basically measure these chemical changes, and then we can link those to the stressors that we're measuring. So acidification, hypoxia, nutrient pollution, turbidity, and metals, to understand which of these stressors are driving changes in reef health or reef metabolism. Hawaii Mesonet is a weather monitoring network that's run by UH and the Water Resources Research Center. We have about 100 stations located across Hawaii. And the stations here on Maui are really kind of spearheaded by Chris Schuler. And after the fires, one of our major concerns was the release of contaminants to the coastal ocean following rain events. So we use this weather station located just south of Lahaina Luna to monitor coastal precipitation over the winter and to guide our sampling events. This is a figure that shows the 5-minute precipitation data from that weather station. So precipitation here since October and through January. And the green is all of the precipitation measurements. So the black lines are when we sampled. So we sampled once in October and in November, which were not associated with rain events. We sampled in December. We were expecting a little bit more rain, but it turned out, fortunately, that there wasn't very much rain here. And then you probably remember or know, if you live on Maui, that we've had quite a bit of storm events and kona winds during January. And so we have a number of different rain events here, but we sampled this big one in the beginning of January. And then we had one more towards the end of January. Okay, so I'm gonna jump into some nutrient data and then the metals data. This slide is summarizing nitrate concentrations, and as a reminder, nitrate is often associated with fertilizers and wastewater, as well as runoff. The map here is showing nitrate concentrations, where higher nitrate concentrations are shown in the darker pink circles. So we see higher nitrate concentrations closer to shore, and then a decrease in nitrate as you move offshore. This is to be expected because our nutrients come from land. We see higher nitrate concentrations associated with the streams, Kaua'ula, Kahoma, and Wahikuli. This is also something that we would expect to see. The figure here on the right is showing nitrate concentrations at each of the sites, ranging from north to south. And then each of the symbols indicate the different months that we sampled. So blue is October. That was the closest time to the fire. Orange is November. Yellow is December. That was the small rain event. And then January during the big rain event is shown in purple. So we do see higher nitrate concentrations following the storm event in January. Again, this is to be expected. We don't, one thing I should mention is that this is actually, this black line is the Department of Health water quality criteria for open coastal waters, the wet criteria. So we do see that most of our sites exceed this criteria. This is not totally, I mean, this is something, our waters on Maui are eutrophic, and Hui o ka Waiʻola has shown that nitrate does exceed the DOH limit. So I'm not super surprised by this. The numbers are a little bit higher than I expected, but we don't see any strong evidence for higher nitrate concentrations within the burn zone. We usually measure nitrate with phosphate, and so here I'm also showing phosphate concentrations where the dark symbols represent higher phosphate concentrations. These concentrations are fairly low, nothing too out of the ordinary here. We do see higher concentrations again associated with the Waiikuli and Kahoma and Kaua'ula streams. And then the figure on the left is showing higher concentrations after the January storm event as well. There isn't a DOH limit for phosphate. I think there's a DOH limit for total phosphorus. But like I said, there's nothing too out of the ordinary with these concentrations. Nutrients are associated with land-based sources of pollution, like fertilizers and wastewater, but metals are contaminants that we can associate with urban infrastructure. And in particular, copper is associated with anti-fouling paint, so boats, for example. This figure is showing copper concentrations in parts per billion, where the darker colors represent higher concentrations and the lighter colors represent lower concentrations. So we do see elevated copper within the burn zone here relative to these two control sites. The figure on the left is showing copper at each of the sites for each month. So starting from Kahikili to Olowalu. We do see elevated copper concentrations, particularly at the harbor and post-fire. So the first sampling event closest to the fire, the time of the fire, is shown in blue. And then we see those concentrations slowly decreasing over time. So this purple symbol is the January sampling event. At the harbor, these levels did reach chronic and acute toxicity for aquatic organisms, as determined by the EPA. Like I said, these concentrations have been declining over time. We do expect to see higher copper concentrations in harbors because of boats and anti-fouling paint. So I think moving forward, it's probably important to continue to monitor copper concentrations, particularly within the harbor. I do want to mention and emphasize that these high levels were very localized to the harbor. So to give you an idea of where we were sampling, the harbor site was literally inside the harbor. And then our ferry pier site, which was several ppb below the concentrations that we measured in the harbor, this site was only, within 50 feet away. So emphasizing that the higher copper concentrations were pretty contained within the harbor during our sampling. Lead is widely distributed in the environment through the combustion of leaded gasoline. It also occurs in household items like paints, pipes, rubbers, plastics. So the figure on the right is showing lead concentrations in parts per billion, where the darker colors represent higher concentrations. And similar to copper, we see higher lead in the harbor and ferry pier. And the figure on the right is kind of showing those individual sites again in individual sampling periods. So elevated post-harbor or elevated post-fire at the harbor, which is these sites, and then decreasing over time with the lowest concentrations measured during our January event. So there's a dilution effect that we're seeing here. And I also want to say that these levels are not considered harmful to aquatic life. Okay, here I'm showing zinc concentrations. So zinc is naturally occurring in seawater. In open ocean or in the deep ocean, concentrations are less than 1 parts per billion. In coastal waters, maybe less than 5 parts per billion. So these darker colors are showing higher zinc concentrations within the burn zone relative to our 2 control sites located north and south. We also are seeing higher zinc concentrations that follow the January rain event. So this is different from copper and zinc, where we saw, different from copper, where we saw higher concentrations of copper that were really kind of close to the harbor and within the ferry pier. Now we're seeing zinc that's more kind of widespread and following these runoff events. Zinc is not as well studied as copper. I think that the EPA limits for zinc are 80 to 100 parts per billion for aquatic organisms, but for corals, like I said, it's not well studied, but for corals, studies have shown impacts at 10 parts per billion, particularly for coral fertilization. So there could be some environmental ecosystem concerns with zinc. Not great numbers, and something to definitely keep an eye on moving forward. Okay, so I know that organic contaminants is also in people's minds, and so I just kind of wanted to let you know where we are with this. There's 2 types of analyses that we're looking at, and when I say we, I really mean Sean Swift, who is Craig Nelson's graduate student and is really leading all of the contaminants and seawater study. So there's the targeted analysis, and this is a modified EPA method that detects specific organic compounds. And then there's an untargeted analysis, and this is kind of more cutting edge, a more cutting edge method, and is very efficient in identifying thousands of unknown chemicals, but requires very expensive equipment. And so what we really have access to is the equipment for the targeted analyses. So this method can target 126 contaminants, including PAHs, PCBs, pesticides, and others. And we'll be using, Sean will be using a machine at UH to run this method. He so far has ran 2 samples, low profile samples, and he did not detect any contaminants except for very low levels of phenyl, benzyl alcohol, and naphthalene. And these levels were not concerning. So he estimates that in about 2 to 3 months, he has some big stuff coming up. He's a PhD student that he needs to focus on. And then he's going to run these samples, and he estimates he should have publicly available data within the next few months. Okay, and so the last data that I wanted to show was some of the sensor data. So this figure is showing oxygen concentrations at 3 of the sites within Lahaina. So Wahikuli in green, Pomana in purple, and Mala in orange. And then our 2 control sites, Kaikili in blue, which you can't see because it's behind everything, and Olowalu, which is in orange. These oscillations represent the day-night cycle of photosynthesis and respiration. And as I mentioned earlier in this talk, one of the things that we're keeping an eye out for is hypoxia, or low oxygen concentrations. These are the classifications for hypoxia on a reef. So less than 5 milligrams per liter is weak hypoxia. Less than 4 milligrams per liter is mild hypoxia. Less than 3 is moderate hypoxia. And then less than 2 is kind of the classic really bad hypoxia. We are seeing consistent weak hypoxia at nighttime. Years ago, I would have thought that this was not good, but I think we recognize now that nighttime hypoxia for short periods isn't totally abnormal. Sometimes these reefs do cross the threshold into mild hypoxia and even moderate hypoxia. But at this time, we don't know what drives this. We're also seeing, this kind of mild hypoxia at Olowalu as well. So at this point, we don't think any of these trends are related to Lāhainā Wildfire. One thing I do want to bring your attention to is this section of the data here, which is from the big runoff event that we had in January. This is that data section blown up, and here is the period of time associated with the big storm event. So at all sites, we do see reduced photosynthesis. This is likely due to enhanced turbidity, which blocks sunlight on the reef. We're seeing that respiration is maintained, so potentially the addition of organic matter through runoff helps to drive that. And then the period of nighttime hypoxia is also extended, and we can really see that at Olowalu. So more hours of low oxygen at nighttime. So if there were an event that caused several days of runoff, reduced circulation, to increase residence times and high turbidity, it's possible that these type of hypoxia events could be worse. So the reef metabolism data that we have is really going to try to help us understand how these short periods of extended mild hypoxia affect coral growth. To summarize our main findings so far, we see elevated nitrate concentrations across most coastal West Maui sites, both inside and outside of the burn zone. These levels are not great. They're definitely worth monitoring, but at this point, we can't see that it has anything to do with the fires. It will be, I think, important to compare to historical data, such as the data from Kealoha, to see if we can see any changes in time. We do see elevated copper and zinc, with elevated copper levels being very localized at the harbor and right after the fire. Elevated zinc levels are a little bit more widespread and definitely worth monitoring in the context of ecosystem health and coral health. And then we have observed that runoff and high turbidity extends these periods of mild or moderate hypoxia, both at the Lāhainā sites as well as the control sites outside of Lāhainā, well, specifically Olowalu. To outline the next steps of our work, we aim to have more data on organic contaminants in seawater in the next few months. Eileen, who is, I think, on this call, is leading a study on contaminants in fish, and she will be working closely with community members on this study. And so we can put my email and her email in the chat if you want to connect about that work. I know in particular, she's hoping to connect with fishermen in Lāhainā. We have the stressor data, on hypoxia and acidification and metals. So our next step is to really connect those data to measurements for ecosystem metabolism and that reef health metric. We're also in discussions about the best way to provide this data to the public. So which repository do we put it in, and how do we help to visualize it for the community? And then, of course, we're working with partners to develop a strategic long-term monitoring plan for water quality and ecosystem health in Lāhainā. And I'll just end by mahaloing our students and also Greg, who is the lab tech at Maui College Water Quality Lab. These are really the people that have done all of the legwork, getting out there in the rain and to sample, and are running all of the samples in the lab as well. So huge mahalo to them. And with that, I will stop sharing my screen. Can you?
Thank you, Andrea. So we've got a few minutes for Q&A, and forgive me, we have like a slew of questions, and then your team has been like diligently typing out the answers. So we've got some already answered and then some open. So what I'm gonna and a few minutes left. So I'm gonna do my best. I'm actually gonna go through the answered ones, the typed ones. I'll read it out. And if you have any extra comments that you want to add to your team's answers. So will analysis for PCBs look at all 209, cogeners or a more limited subset? And so the answer was it'll be a limited set. We're following a modified version of an EPA method, which is EPA 525.3, which includes 14 types of PCBs as target analytes. It's possible we would be able to detect additional cogeners if they were there, but we don't know for sure. More details on the method are available on the EPA website. Anything to add to that? That was sufficiently answered. Okay, great. Thanks. We have so interesting to see Mala Point so clean compared to the contaminated areas directly adjacent to it. I presume this is a product of strong currents in the area or flushing, and likely responsible for the high biodiversity we see in the area despite being next to a boat ramp and a major drainage ditch. And all they said was agreed, but do you have any extra?
Yeah, no, I agree. Like we see when we go just a little bit offshore, any kind of higher nutrients or copper or whatever levels, they dissipate very quickly. So I would agree that, the ocean is doing what it's supposed to do. It's flushing.
Gotcha. Okay. The next question was, are your metals measurements dissolved or total? And Craig replied that it was dissolved. I think that's pretty self-explanatory. Will the Oluwalu sensor continue to be considered a quote control sensor going forward/post TDS operations that began in mid-January? So the answer was we consider it a control for the fire impacts. All sites differ in runoff, nutrients, etc., but Oluwalu and Kahikili, I believe, south and north of Lahaina, respectively, are good controls for the specific impacts of the fire.
Yeah, and we pulled the sensors out on February 1st, so the sensors are not out anymore.
Gotcha. Okay. Uh, a very open-ended question, and I think you did touch on it earlier. But what causes an upwelling? If we could kind of recap a little bit, what causes an upwelling? It's a good question. Many things hard to answer here.
Like that's an entire lecture. Yeah, I mean, I think yeah, a lot of different like physical processes in the ocean. We often see them on the western sides of places, eastern sides of oceans. It has atmospheric like conditions drive upwelling as well as oceanic processes.
Gotcha. Okay. Sorry if I missed it, but is this data published or will a report be made public to summarize the findings? Craig replied, we are publicly releasing data as it is ready.
Yeah.
Okay. Can DOH help expedite the testing? DOH doesn't have the equipment and expertise to support the majority of these analysis, particularly metals and complex organics, and are also focusing on drinking water and additional priorities, but certainly they may be able to offer more details.
Yeah, and we are also working closely with DOH on how we're collecting the data and understanding what the data mean and things like that. So yeah, they've been a great partner in the project.
And have you found any other examples of nightly mild hypoxia on reefs with higher coral cover? Could this be a proxy for the amount of respiration on the reef while photosynthesis is not happening? The answer was absolutely. We find a lot of nighttime hypoxia on, quote, healthy reefs, even pristine, robust reefs far from people. What we are looking for here, as you had emphasized throughout the presentation, are extended hypoxia events, which would be many hours or days, localized near the fires.
Yes.
Okay. What machines in particular are you using to do the targeted analysis, and what machine or machines would you need to do untargeted analysis? And so it says we're using liquid chromatography tandem mass spectrometry, geez, primarily triple quads and Orbitrap electrospray ionization machines. We have good access to machines, but it does take time. Hope I
Yeah,
didn't slaughter too much of that. So-
I probably would have said it the same way.
okay, great. Um, okay, so unanswered questions. Does the elevated iron it oh oh I think they're still like typing them. Your team is awesome.
I know they
There's so
are.
many. Okay, I'm just gonna our fish caught off of Maui safe to eat.
I'm gonna hunt that to Eileen. Eileen,
Hear me?
yes.
Sorry, I was starting to type responses for that
Thank
and
you. You're
I
amazing.
thought that one's a little bit difficult to tackle in untyped answers. So, um, in brief, we don't have the information to say that yet or not. It's definitely, I think, at the forefront of everybody's minds when you think about problems, especially for human health resulting from this. And so it's something that is a priority for us. We have been working very hard to get the support needed to actually do those analyses, but to do the kind of comprehensive analysis to give something like a fish advisory and to say definitively, what the health impacts could be, that requires a really comprehensive set of sampling. And so that's something that we are very actively working on addressing, but just to sort of caveat that as well, it's much more achievable to say these fish present a risk right now than it is to across the board say all fish are going to be safe to eat. So the result even of a comprehensive study is more likely to be sort of recommendations on things to potentially avoid or for vulnerable populations. So yeah, it's a complicated answer, but we're working on it.
Thank you. We appreciate, shedding some insight into that. One of I started to read and then it was answered, so it moved screen. Does elevated iron from wildfires affect fish populations? Thinking about the rogue projects of ocean fertilization. So the answer was any types of elevated metals, contaminants, etc., may affect the health of fish, but iron is not something that is typically a priority concern when we think of contaminant impacts on fish. That said, we also lack a lot of data on the impacts of metals and other contaminants on the health of fish themselves, especially when exposed in combination. This is a great question and something that we can think about going forward. Okay, did this one. Let's see. I think this is something on everyone's mind, and very similar to the fish question. So I imagine it would be something along the lines of that answer. But should we stay out of the water until more data is collected? Would our coast benefit from a break from this additional human impact? Is it maybe just safer to kind of wait and see, or is it just by personal preference?
Oh, yeah, I mean, the data that we're collecting now, we're not looking at it in the context, we can't analyze it in the context of human health, right? Like the levels that we're seeing associated with some of the metals so far are not higher, what we would consider harmful to human health. So I would just say, we're going to get the organic contaminants data in. I go in the water. I think that that's like a decision that you have to make on your own with whatever you're comfortable with. Yeah.
Thank you. Okay, another one that just got answered. Sorry if I missed this, but might you expand Oluwalu monitoring given move to have it as the temporary dump site for Lahaina waste? And the answer is there are a couple groups of collaborators focused on sedimentation and runoff impacts on Oluwalu. So we hope to incorporate those studies with further investigation of watershed impacts.
Yeah.
Yeah. And a lot of these are, many of these are kind of like the human impact side. So like you mentioned, right, like you kind of have to decide for yourself on that. Okay, we are right up against it. And then I have another question. Okay, I'm going to go ahead and share those 2 email addresses in the chat for further questions. And let's see, this last one. Will you be testing edible portions of fish or exposure in other parts as well? The answer was edible portions are always a priority, but also testing less frequently consumed portions, for example, the liver, is very useful for understanding how contaminants are being transferred through the ecosystem and potentially accumulated. Okay. Well, thank you very much, Andrea, and all of your colleagues for coming in and answering all of the. Actually, that was really helpful. We had a lot of questions, and I wouldn't be, we wouldn't be able to get through them if not for the amazingness of your team. So, like we mentioned, the 2 email addresses are in the chat. For if you have any other further questions or just want to learn a little bit more about the work that they're doing, but that is pretty much it. So thank you, Andrea, and all of your colleagues for being here tonight and for answering our questions. To answer one of the other questions that came through, for everyone who tuned in tonight, thank you for being here. And yes, this happens monthly. It's a different topic every month. So unfortunately, we won't have Andrea next month. It'll be somebody else, but it does happen, like I mentioned, the first Wednesday of every month at 5:30 on Zoom. Again, mahalo to County of Maui for helping us to put this on. Our next Know Your Ocean Speaker Series talk will feature Mark Hickson. He is a professor and endowed chair of the Marine Biology School of Life Sciences at the University of Hawaiʻi, Mānoa, and part of Fish Pono, our good friends at Fish Pono. And Mark will be sharing his work with our partner organization, Fish Pono, which works to protect our reefs by protecting its caretakers, our native fish species. So keep an eye out for our Reef in Brief newsletter for our April talk. We always give out, we send the registration link out ahead of time. So if you're not signed up for that, you can just go to mauireefs.org to get on our mailing list, or I believe scroll back to the very top of the chat and the link should also be there. And if you want to learn more about us, like I mentioned, please visit mauireefs.org if you'd like to support us so that we can continue to have talks like this and to care for our coral reefs. We appreciate all of the aloha from our community. And again, like I mentioned, we are recording this session, so give us a few days and we will have this up on our YouTube channel, a link to it on our Instagram profile. And again, if you're on our mailing list, we do send out, and in case you missed it, link to the recording so that you can play it back later on. So last but not least, we want to thank our sponsors, our partners, but mostly we want to thank our supporters like you. We had such a great turnout tonight, and we're just really encouraged that there are so many people out there who care about our environment, who care about our reef. So thank you guys most of all for making these talks possible, and we invite you to join us next month. But until then, mahalo, aloha, ahui ho, and thank you for joining us. We'll see you all next month.
Thanks, everyone.
Thank you.